Hello students. So we are now going to discuss the final source of radiation, and that is the neutron source. And here in this figure you can see a neutron is bombarded to a uranium-235 nucleus, and this uranium-235 nucleus converts into uranium-236, and this uranium-236 starts vibrating because of the extra energy that it gets, which destabilizes it. And then because of that, if the energy is sufficient, this splits into two different fragments with the emission of neutrons and energy. So there are different types of neutron sources. First one is the spontaneous fission. Then you have radioisotopes which undergo alpha N reaction. Then you have photoneutron sources. And finally you have reaction from accelerated charged particles. So we are going to deal with each one of them step by step, one after another. So let us start with the spontaneous fission. Some isotopes undergo spontaneous fission with emission of neutrons. So the most common spontaneous fission source is isotope californium-252. So californium-252 and all other spontaneous fission neutron sources are made by irradiating uranium or transuranic elements in a nuclear reactor. So the radiation from the nuclear reactor irradiates either uranium or transuranium elements and produces spontaneously decaying species which are spontaneously fissionable. And then the neutrons that are coming from the nuclear reactor are absorbed in the starting material, and the products that they form, they are basically spontaneously fissile, and then they produce fission reaction and the production of neutrons in the process. A neutron source that is used typically in nuclear laboratories is confined in a cylindrical cavity with a diameter of 1 by 4 inches to 1 by 2 inches and a length of 1 to 2 inches. A typical Californium-252 nucleus neutron source emits around 107 to 109 neutrons per second and a half-life of 2.6 years. So that means the neutron output drops by half in 2.6 years. Here it is shown, since in a fission experiment several neutrons are produced and all these neutrons are of different energies. Here is a graph shown between the neutron energy and the intensity. So you can see that there is a spread in the uh, energy with respect to intensity. Maximum intensity is for around 1 MeV neutron, and there are different neutrons with different intensity coming out, and all these neutrons are having different energies. Like for 4 MeV neutron, the intensity is around you can say 9T in the arbitrary units that are shown in this graph on the y-axis. Then you have radioisotopes which undergo alpha N reaction. That is, for example, an alpha particle is targeted to a beryllium-9 nucleus. It produces a carbon-12 and a neutron with a Q value of 5.71 MeV. So what happens is any alpha decaying source or an alpha source is mixed with beryllium or any other suitable target, and then when they are mixed, then in that case what happens is alpha is absorbed by beryllium and neutrons are produced in the process. So you can see here alpha particle energy versus the neutron yield. And from this graph, you can see higher is the energy of the alpha particle, higher is the neutron yield in the case. So alpha beryllium neutron source may produce about 30 neutrons per 106 alpha particles. The useful lifetime for such sources depend on the half-life of the radioisotope. So the radioisotope's half-life determines the lifetime for a neutron source. The size and the cost of these neutron sources are comparable to spontaneous fission sources. So the combination that are usually used are plutonium beryllium or americium beryllium or americium lithium. Then we talk about photoneutron sources. And what are these? Basically, gamma rays with energies exceeding the neutron binding energy in a nucleus can eject a neutron. And this process is known as photodisintegration. Two examples are, if beryllium is targeted with a photon of 1.7 MeV or greater, it produces one neutron and two helium-4 nuclei. Similarly, a deuteron or deuterium, when it is incident with a photon of 2.26 MeV or greater, produces one neutron and one proton. Now, the disadvantage of photodisintegration or a photoneutron source is that a large gamma ray intensity is required to generate any sufficiently intensity neutron source. Any neutron source with any reasonable intensity requires a large gamma ray activity for photodisintegration. So as it is shown here, about one gamma ray in 105 to 106 interact to produce a neutron. So a large amount of gamma ray intensity is required to produce smaller intensity neutrons. And so when you're talking about neutron intensity, there is a background of gamma rays which are coming out which haven't interacted at all. So a background of gamma ray is also there along with the neutrons which come out in these sources, photo disintegration sources. Another type of neutron source is the reactions from accelerated charged particles. So what happens is, two accelerated charged particles like a DD reaction, two deuterium, when they combine, they fuse and form a helium and a neutron, and an energy of 2.26 MeV is the Q value. Similarly, DT reaction is also there where a deuteron combines with a triton to produce a helium-4 and a neutron. Now these are fusion reactions, and the Coulomb barrier between the incident neutron and the light target neutron nucleus is relatively small. Why is it small? Because the charge of these nucleus species is small. They are lighter nuclei with a small charge, and so the Coulomb barrier, which is going to prohibit the fusion of these two nuclei, it is very small, so a small energy is required for the incident beam. So almost around 100 to 300 keV potential is required to accelerate the deuterium ion, and that much is sufficient for the fusion reaction.